So let's start. So today the topic is make build automation. This is another entry in our little series on software engineering for beginners. And oops, sorry. You already know this slide. It's one aspect of software engineering is software configuration management, and build management is again one task within software configuration management, and this is the topic of today. Again, as always, what are the benefits? So why should you care about build automation or build management? The main reason for the average user is you want to allow that people can compile the software, including yourself, without detailed knowledge about the toolchain details. So you want to support multiple toolchain, then probably your code needs specific flags. You want to allow compiling the software without source code internals and without knowledge about target system internals. So you want to ease the compilation across a variety of systems. This is mainly all about automation. Yeah, I think starting with 2-3 source files, it's just not feasible anymore to carry out all those steps by hand, and it's also error prone. So if you have a real software project, at some point you need a build system. The second aspect is to reduce build time. And when you have a smaller software project, that's probably not a big issue. But if you already had the fun to compile a large community code like OpenFOAM, or there are other large codes, this can take hours in the worst case. And this is an initial build. Now, if you consider if you are developing, you make changes in the source files and then you want to recompile. And so it's important that the build system is really optimized, that it only recompiles the files that changed and all the files that depend on the change file. So dependency management or dependency tracking is a very important part of that. And for software development, the build dependencies must be reliable because you have to trust them. Nothing worse than if you debug a code and you change something and you build it, and then your change is not in the build because the dependency tracking doesn't work. And finally, of course, parallel builds. As we all know, modern architectures are mostly providing the performance through parallelism. And so you want a build system to exploit this parallelism. Finally, the third reason why a build automation system is essential is you want to enable what is called deterministic compilation for reproducible builds. This sounds a bit strange in the beginning, but this is a non-trivial part. So you want to select and configure a set of external dependencies that is compatible. And for large codes, this can be really difficult. So codes that depend on a lot of external packages, and then those codes, those libraries probably depend again on other dependencies. Then maybe the code is not compatible with all versions, but you need a specific version and you need to configure it with specific settings. So this really can be a hard problem, and everybody who tried to compile large software project knows that you can even fail. So it can be impossible to build such a code. And so this is a major task to make this as easy as possible. Then, of course, another task is to configure the source files for a specific feature set. So sometimes you don't need all source files, and to select a compatible set of source files so that it actually compiles. And nowadays, everybody talks about continuous integration, continuous testing. And in this context also, it's crucial that the build is reproducible, that you can trust that the result of the build is always the same, that this is something that's reproducible. So to wrap it up, the benefits are automation. That's, I think, the first thing you think about. Then portability, speed up, and finally configuration, to manage the configuration. So some history, you may know me, I always like to see this also in a historic perspective. In the early days of Unix, Build systems were collections of operating system specific shell scripts. So the automation was done by shell scripts, and all the commands required to build the code were in those shell scripts. And this was actually also the starting point. And you can see that with Make. It has some aspect that reminds you of shell scripts. The first Make tool, as we know it today, was implemented by Stuart Feldman. He worked at Bell Labs at this time, 1976. It then got a POSIX standard, and there are multiple implementations available. I don't know the exact motivation, but I guess he wanted something that's more specific or more generic, especially, because those shell scripts were tedious to maintain, and he wanted something that's more generic. What I don't know is how this first Make implementation looked like. I guess that the main concepts were already there, but it was probably not Make as we know it today. For implementations that are available, there is BSD Make. This is probably quite close to the POSIX standard. And then there is GNU Make. And as always with GNU tools, this is not compatible. So GNU Make has a lot of extensions, useful extensions. And nowadays, when you talk about Make, what you actually mean is GNU Make. And this is the standard Make on Linux as well as on Mac OS. There is also a Make implementation on Microsoft. I don't know how widely used it is, but it's still there. It's called NMake, and this is part of Visual Studio. There were a lot of efforts to replace Make in the past. So some of you still may know SCONS, and there is Rake. All of those had the motivation that they wanted the makefile to be a script file and to have in there all capabilities that you have in a real scripting language. Of course, you can use shell scripting in the make file, but as you might know, shell is not very portable, even within Unix operating systems. And yeah, so to have a scripting language that is more robust across different platforms and portable is probably a good idea, but none of those really succeeded in replacing Make. Yeah? So Make is still there, so it seems to be a sweet spot in a domain-specific language, similar to SQL. Yeah, also in SQL, people said it's dead, but it's still there. There are also more modern replacements. While investigating here for this talk, I found that there is the Ninja build tool, is optimized for speed by Google. They use it in Android and Chromium, and that's really mainly optimized for very fast dependency generation on recursive and rebuilds on recursive builds, yeah, for development. And then there is a second flavor of build tools, and those are not build systems themselves, but those are build file generators. So they create then the local build files. And one early example is GNU Automake. When in the early days, when I did my PhD, all open source software was with what is called auto tools. Yeah? It was pain, but this was how you did it. Yeah? And that was the right way to do. And so nowadays there is a successor, CMake by Kitware, again, also a build file generator. I have some slide at the end of the talk, what I think about CMake and yeah, my opinions of that. Maybe we can discuss a bit about that. And there is another solution that's probably not that well known anymore, QMake, which was already available before CMake. At that time, probably by Trolltech and now by the Qt Foundation. Modern languages, or modern compiled languages, I have to say, usually bring their own build tool, and examples are Golang and Rust. So they have, as part of the main implementation, have an integrated build tool, and mostly closely connected to a package manager. Yeah? So yeah, there you don't need Make. And at least for Golang, it works pretty well. Yeah? You don't have to write a makefile, and still everything works as intended. So now, there is one core concept that is the crystal of all makefiles. Yeah, this is the minimal thing that must be there in a makefile. So Make is controlled by makefiles. Those are text files, and those specify what needs to be done. And a makefile consists of so-called rules. A rule is a target, then a colon, and prerequisites. Targets can be multiple, but usually it's one. And very important, the assumption or the core idea behind this is that target is a file to be generated. Prerequisites are the input files that are used to create this target. And then in the next line, and this is now very important, therefore I have this here in capital letters, the syntax of make is that the first character here is a tab. Very important, otherwise it will not work. So this needs to be a tab, and then come one or more recipes how you create the target from the prerequisites. Of course, you do not need to use all prerequisites, but somehow the prerequisites are related to the target. So the actions you need to carry out to accomplish this step. Again, target and prerequisites are assumed to be files. And this thinking in files is very important, because when you design your makefile and think about how you can implement something, it's important that in the core concept, make assumes that those are files, that target and prerequisites are files. In some cases, a target may not be connected to a file. Those targets are called phony targets. I come to that later, how to deal with them. Just already that you heard it, there are targets that are not related to a file, but they're really only used for very specific things. And when you implement your makefile, I recommend to try to keep everything, all targets, that they are represented by files, and then you will have no problems. So this is the most simple makefile. And it consists of rules, as mentioned. It's a C program. The first target is called edit. And when you look at the action, this is the name of the binary. So this is a file. And then you have prerequisites. In this case, all the objects that are necessary to link your executable. Then, of course, you need to tell make, well, the prerequisites, those are somewhat intermediate build results, how to create those objects. And so you have, in the simplest case, one rule per prerequisite. For every object file, you have a rule telling make, okay, how can I get there from one of the source files? And of course, here in C, you have the source file as a dependency, as a prerequisite, but then you also have all the headers that are included. So that if you change an interface, a signature in a header, that make knows what files it needs to rebuild. And finally, at the end, you have one of those phony targets. So, for the rule, one important thing is the action is only executed if the target does not yet exist. So this is on the first build, or if one of the prerequisites is more recent than targets. And this is purely done on a file modification basis. So make doesn't care if you actually changed anything in there. It's just the file modification time that's important there. Yeah, that's taken into account. So down here you have this clean target with no files. So there is no clean file and no prerequisites. This is one of those phony targets. The problem here is, in this case, on the next slide, we have a solution that to this per default, because make assumes that this represents a file. When there is a clean file, for whatever reason, in the directory, this action will not be carried out anymore, yeah, because the clean target is already there. Why should it re-execute it? Default is when you call make without any arguments, it will generate the first target in the makefile. In this case, the first target is the edit target. Yeah, so when you just call it make, then it will go through the makefile, and the first target it finds is the default target. Of course, you can call make with any target as an argument. For example, you could say, of course, make clean, but you could also say make command.o. That also would work. Yeah? And then make would execute if required. Yeah, so if it's required to be rebuilt, this one and all dependencies, yeah, that are necessary. So now the first improvement we can do in this makefile is to use variables. And this works very similar to a shell variable. So you can define a variable, in this case objects, with the list of objects, and then we can use this variable in our rules. And as you see, this simplifies the makefile a bit, but it's still kind of verbose. Yeah? So this is not the end. Some behind the scenes knowledge, and this is difficult to understand in the beginning. The make language is not a sequential or procedural language. So make doesn't interpret this line by line, and this is how it gets executed. Actually, what happens is make operates in two phases. In the first phase, it reads in all the make files, and it builds a dependency graph of all the targets and their prerequisites. And so you could see it's like a state machine. Yeah? So it collects all the information and builds this dependency graph. That's the first step. And then in the second step, it uses this dependency graph to determine which targets need to be updated. And it runs all the recipes to do that. Yeah? So to update them. So this is how it works. And this is very important to understand. And the difficulty comes mainly with those two steps when variables get expanded and in which order. Yeah? And this is the main thing you need to understand to master make. So now the first real trick to make it a lot simpler is by using so-called implicit rules. So make is very clever in deducing how targets are built, and it has a lot of built-in rules. So for example, it knows very well how to get a main.o, an object file, from a source file. And you do this by omitting the recipe and just specifying the dependency without the main.c dependency. So main will now search for a source file that it can match against a known rule. In this case, a rule how to build a object file from a C source file. Of course, now you could ask the question, well, what if I have many main files? Yeah, one C++, C++ main file, one C file, and so on. What happens then? I'm sure this is well specified, but I don't know the rules. But let's assume it's simple and there is only one main C file. I mean, you can try it out yourself. The built-in recipe is documented. So all the known implicit rules are well documented, and they are controlled by variables that are used. And you can influence what happens there in this built-in rule by setting those variables in your makefile. Of course, now this reduces the file a lot. You only have the dependencies. One thing I want to mention here, okay, let's first do this phony special target. You have some special targets, and one is this phony target. And with this phony target, you could say you can tag targets as being phony, and this means you tell make that those are not related to a file, and this causes that they are executed, or the recipes, the actions are executed, whatever. Yeah. So even if there is a file clean, it ignores it. Yeah? So you tell it, okay, look, this target is a phony target and it's not connected to a file, just execute it. Yeah? Another thing is this vpath variable. This is a special variable, and it specifies a list of directory that make then uses to search for targets and prerequisites. By default, it will search in the current directory, so where you call make. But in many cases, you want the source files maybe not in root, and you want probably maybe the source files in different directories. And by specifying all those directories in vpath, you can automatically let make search in those directories for targets and prerequisites. So this is very handy. There is one further simplification maybe you can do. I mentioned you can have multiple targets on the left-hand side as long as they share the same prerequisites, and this is done here. Yeah? So here you put together all the objects that depend on a certain prerequisite. now you would say, okay, but KBD are now 2 times here. Yeah, that's right. And that's allowed because make builds a dependency graph. It will pick up all those rules, all those targets, and add them to the dependencies. Yeah. And well, some say this is not a good idea because it somewhat makes it more complicated. It's up to you, but it's possible. Yeah? So you could have here multiple targets on the left-hand side for those implicit rules. Now comes the real power. You can write your own implicit rules. This is called pattern rules. So a pattern rule allows you to have a custom implicit rule. And this is usually what you want. And this gives you then the power to really automate everything in the makefile. And I come to some requirements. What you want at the end is you want to implement a makefile once and then leave it as it is. And it should work for your project in the future. Yeah? So you don't need to touch it anymore if you don't change your requirements. So this is an example for the pattern file. And this is actually the pattern rule for the implicit rule built into Make. Yeah? So this is a rule how you build object files from C files. And I already showed this to you. Make sets some so-called automatic variables that are predefined variables. Some of them are related to the current rule context you are in. Some are related to the make execution. And it's very important to know those variables. Again, they are well documented. And when you ever have a problem to solve in Make, a good idea is always to look what automatic variables Make offers to you. And this then gives you maybe an idea how you could solve a problem. In the rules, the most commonly used automatic variables are $@. This is the file name of the target of the rule. So essentially this part here. Then $smaller is the name of the first prerequisite. Of course, there are more here. Yeah. So for example, getting all the prerequisites. And finally, $, it's not used here, but we will use it in the template makefile, is just the stem with which an implicit rule matches. Yeah, so with which the pattern rule matches. Yeah, so just the stem. This means just this part. Yeah, just this pattern. And this is what I most commonly used. In rare cases, there are more of them. And again, it's documented. You can look it up in the documentation. Now, a few words about variables. How to set variables in makefiles. First, the shell environment variables are also valid inside the makefile. So when you set variables in your shell, you can use them and they are used in the makefile, within the makefile, similar to a shell script. Then, as mentioned, Make sets many automatic variables. So there are a lot of predefined variables. Variable names can contain functions. Function is something like that. It's written similar to a variable reference, but then you have this function name and function arguments. And I show you later other functions that you can use, or also other variable references. So a variable can reference to another variable. And there are a bit complicated rules how those get expanded because there are different types of variables. To set a variable that is not already set, you can use this != operator. This is, for example, useful if you want to allow a variable to be overwritten by an environment variable. So you set a variable, but using this operator, you allow that someone in the environment calling make specifies it in the environment. This allows you to set things from outside without editing the makefile, for example. That's one application of this operator. Then the shell assignment operators, ! equals. This allows you to set the variable to the output of a script like this. And well, some think that this is not a good syntax, so there is an alternative syntax, and this is the shell function. Yeah? It's up to you what you like better. And finally, you can split long lines with a \ character. The \ character inserts a space. Sometimes you don't want that. There is a solution for that. So there's a special version of that that doesn't insert a space character. There are two basic types of variables. The default type are recursively expanded variables, specified, defined by a simple equal operator. So here in this case, your reference include dirs, and this will expand to I foo I bar dash capital O, as expected. This is fine. This usually behaves in a lot of cases as you want it. The disadvantage is this doesn't allow something like that you say, okay, I want to add to C flags. So I specify C flags equals C flags dash O. This is an error. Make will give you an error with that because it creates an infinite loop. There is a solution, and the solution is the plus equals operator. Please read it because in the documentation, I don't have a separate slide on this. There are some subtle issues there. Yeah? What happens when you use this operator on a recursively expanded variable? Another disadvantage is that functions that are referenced in the definition of recursively expanded variables, execution can get very slow because those functions then get evaluated anytime you expand the variables, and this then can be very often. Yeah? So be careful using functions in recursively expanded variables. The second type of variables are so-called simply expanded variables, and they are defined by colon equals. Those get set at the time where the variable is defined. Like here, you set x to foo, and then you say y equals x bar, and so y is foo bar. And when you later on override x, this has no effect on this y variable because it will only be expanded once at the time where a variable is defined. There is another aspect I will not touch in detail, just that you know. It's also important where the variable is used, yeah, in the target or in the prerequisites or in the recipes. And how make calls this is immediate versus deferred expansion. If you have any problem with variables, you can read it in there. So first, when does expansion happen? While parsing or when using a variable? And it also depends where in the rule the variable is used. If it's an immediately expanded variable or is it a deferred expanded variable? This now sounds all very complicated. I guess this is the price to pay that it is a programming language somehow, a domain-specific language. Usually it works out well. Yeah, so usually when you don't do crazy stuff, it works out well. But I have to admit, there are cases where the makefile doesn't do what you wanted to do, and it can be difficult to find out why things don't work. Yeah, I don't want to, to not mention this. Yeah. Now for functions, as already mentioned, they are specified like a variable reference, and then you have the function name and you have function arguments as a list. Details on usage will follow in the demo, so I only show here some of the functions. Of course, there are a lot more. There are tons of functions. Most of them do portable text processing. Of course, you can get away with doing everything with shell tools. So you can use shell, and with set, awk, or whatever, you can do all kinds of stuff, find, and so on. But the best practice recommendation is use those make functions because it is more portable, probably faster, yeah, because you don't have to create a process. And so it is recommended to use those functions. Most of those functions are specific to GNU Make. But the advantage is, of course, it will be portable. So it might be also that this make file then works very well also on a Windows system, yeah, because those make functions just are portable. A lot of those functions operate on whitespace separated words in text, yeah, because this is a common use case. You have list of files, list of targets, whatever. Usually you have lists of strings. And so a lot of those functions per default operate without needing a loop automatically on white space separated words in text. Those are just some common functions, just to give you an idea what's available. So pet_subst allows you using a pattern to match parts of the string in text and replace it with replacement. And we will see an example in the demo. And this is a special version for the task of replacing file suffixes. Because this is so common, you use this a lot in Make, you often need to replace file suffixes. Then there is this shortcut syntax where you have var :suffix equals replacement. And those are just the file endings. Yeah? So the file types. And then you have filter. This matches the pattern. So you get back a list which matches the pattern. And filter out will give back what does not match the pattern. Wildcard does what it tells you. It matches a list of files similar to shell when you use a pattern or ls star something, and this is very similar. You can match a list of files. And finally, you have those special functions, error warning info. Those are expanding whatever is text, can be variables. And in case of error, make will exit at this point. So it will exit at this point in the makefile. Warning will just output the text, but make will go on, but still will tell you where it was called, and info is just to output text. The error and the warning function are quite useful to debug make and to output the value of variables. So if you think something went wrong, like a target was not called or something, then you can just do printf debugging using those functions. Make also has conditionals, and the following different variants are available. There is if not equal, if equal. There is some problem with surrounding white spaces because make will take sometimes surrounding white spaces into account. To prevent this problem, a common practice is to use the strip function, to remove surrounding white spaces. Otherwise, it will not behave as intended, because you don't see the white spaces, but they are still part of the string. There is one additional flavor of conditionals. So there is if equal, if not equal, and then there is if def and if not def. If def checks if a variable is set, but it does not check if it is empty. So you could ask, okay, what's the difference? Well, in this case, it could be, or in the equal case, it could be that CC is set to another variable, and this other variable is empty. So this means this variable is set, but it's empty. And therefore, there is this distinguishing between those two cases. And very similar to any programming language, of course, you have an else clause that's optional. Now, some requirements, and those requirements are from me. I am opinionated there, and I just want to go through. So this is what I think a production makefile should meet. Those requirements should be met. It should be generic. So you need to set it up once, and no adaptation should be necessary when you add more source files. So you write it, you implement it once, and then you don't touch it anymore. I promote a flat directory structure. This makes a lot of things easier. If you need structuring, don't do it in terms of directories. Do it in terms of file naming conventions. That's a tip. Having tons of directories with just a few source files, that creates all kinds of problems. Use file naming conventions for that. This makes everything simpler. Then the makefile should allow for configurable locations for source header files and also for the make files. It should support a robust and correct automatic dependency generation. You saw in the previous makefiles, you can, of course, specify the dependencies by hand, but this is error prone, yeah, because every time you change something, you need to update the makefile. As you may know, we programmers are lazy people, and so this is very likely to break, and so you want to have an automatic dependency generation. Then, this is one thing I didn't mention, but I will have it in the demo. Per default, make will output the recipe. So just a string representing the command. So it will output the recipe and then execute it and output the output of the command. I want to have a clear output which allows a focus on warnings and errors. Why is this important? Well, for a simple code, this is probably not important. But if you already compiled a C++ code, there you might have build lines which span more than half a page, because there are tons of defines and include paths and lengthy file names, directory paths, and so on. And because not much is in there, probably they will rapidly scroll across your screen. And now when you have those commands scrolling across your screen, when there is now a tiny warning or error, you probably would not see it. Yeah? If you integrate make in a editor or an IDE, this is probably not a problem, but I want also to be able to quickly see warnings and errors, and therefore I do not want to see the command. Still, the makefile should allow me to look at the command, but by default, I want a clean output where I can focus on the warnings and the errors and not on the commands. Then I want a separation of the build configuration and the makefile. So of course you need a configuration, but this should be done in at a separate place. The makefile should support multiple tool chains and or build configurations. So it should allow different variants. Those different variants should be possible to build them simultaneously in the same directory. That's another requirement. And this makefile we provide to you here, we will show, we have a template, created a template for that, should support C, C++, and Fortran, so the popular compiled HPC languages. And it should be prepared for mixed language programming, so mixing C, C++ with Fortran in both ways, yeah. So that the main is in C or you have a program in Fortran. And now I have prepared a demo, and we have a GitHub repository with a makefile template, 3 different versions, and I will do the demo with this template. Still, I encourage you to also look at other repositories which are based on this template. And specifically, this is the bandwidth benchmark. This is a improved stream benchmark, which showcases this template using configuration options. Then there is MD Bench. That's a case which has a special requirement because there we want to have variant builds. So we not only have one main, but we have multiple main variants, and we want to easily build that and in a generic fashion that you can add more variants without touching the makefile. So this is solved there. You can have a look at it. The most complicated and real-world example, of course, is the Liquid makefile. The Liquid, of course, has very complicated requirements. It's a tool, has some dependencies. It is very hardware specific, so it's very specific for the system environment you're in, and therefore, of course, it has a lot of configuration options also, yeah. And so the makefile is quite complex, but still loosely, I would say, loosely based on this makefile template. And last but not least, there is one Fortran example. Those are all C codes. There is one Fortran 90 example, and CG solver, MPI, and core array Fortran variants. And this showcases how you could use this with Fortran. There is some complexity with Fortran, and this is with Fortran 90, you have this mod files. So the interfaces are not just simple text files, but they are generated by the compiler. And this creates all kinds of complexities. There are solutions to that, but not a really good solution. the Intel compiler can create makefile dependencies, but it kind of is useless because you need to have the module files still first, because they need to be there before you build then the file that depend on those. I found this relatively new discussion of those problems, so you might want to have a look at it. In my template, what I recommend and what I do whenever I'm forced to do something in Fortran is I specify the dependencies by hand. Yeah, I think it's feasible. Of course, when you have hundreds of files, this is tedious. And yes, this is again error prone because you might miss out on something, but that doesn't seem to be a good solution to that. If you know anything, just give me a note. For example, this guy implemented a lengthy org script to solve the problem, but I don't know if this is, I think it's over-engineered, but yeah, whatever. So there are 3 different versions. This is the repository I mentioned, where the link is in the slides. And there is a basic version. This is the simplest version you can use as a baseline for your own project. An extended version that allows for a separate configuration of options. And then we have one example for mixed language programming. Let's start with the basic version. So first, for the files, you have one makefile, and then this makefile includes other makefiles. And in this case, you have one include file per variant. The makefile that it's included is specified by this tag at the top. Here in this case, you cannot override it. You might want to write a explanation mark. This is done in the other version, but here you cannot override, which is kind of, let's add an exclamation mark. So I think it's better, and not a question mark, sorry. So here you specify the version you want to use. And now you need to set up this makefile. It's generic. You don't need to change it. It works for C, C++, and Fortran 90. And it uses pattern rules, and it fulfills or implements all those requirements I mentioned before. And I shortly want to go through it to explain how it works. Here you just specify how the binary is called. You can edit this to your liking, and what directories are used. This makefile will use a separate directory for all intermediate build products. So the final build product, of course, is the executable. Everything else is intermediate, and all intermediate build products are in a special directory. So the source file and the root will not be polluted by any intermediate build products. Here you can specify where the source is. Default is the source is in source, surprise, and the include files are separately in source dir includes. Of course, I like to have the headers separately from the source files. If you don't like it, you can set includes here to just source dir. Yeah, it's also possible. And finally, you have this make dir. So if you don't like those include make files to be in root, you can put it, for example, in the directory make and then edit this here. The main feature that enables the clean output is this Q variable. As you can see, you can override it using this question mark. And this at, it causes that the output of the command from make is suppressed. So as you can see, every command is prepended by this Q variable. And this is the at. And as soon as there is an at the start of a recipe, the command is not output. So the default is the commands are not output. Now, when you override this Q empty, then the commands will be printed. And this is how it works. Then we set the vpath variable. I already mentioned it. This will tell make where to search for targets and prerequisites. The nice thing there is that it will match files with the full path. So you don't have to care for complicated paths. Everything that is matched will be then taken in the rule with its full path. So the stem down here, the C, will have the complete path to this prerequisite. And this is quite useful because then you don't have to deal with the complicated paths to your prerequisites. here you see the usage of those functions to collect all object files. And this is done in a generic way. So the main assumption is that all source files are in source dir. Of course, you can create more. And I mentioned I propose to use only one source directory. The things will build faster. It is just easier to handle. Yes, if you have dozens, hundreds of source files, maybe you want to put some directory structure on it, but usually you don't. Yeah, if you have, then you have to extend it here, and of course then search for objects in more directories. Yeah. A wildcard matches all, in this case, C files, and returns a list of matched files, yeah, including the full path, of course. Yeah, so with source dir. Then this is the input for petsubst, and this will replace .c with .o, and in addition set the directory to build dir, because we want, of course, the objects to be created in this separate build dir where all the intermediate build products will end up. And that's it. Finally, to ease the command down there here, I put together all the CPP flags. So CPP flags defines and includes in this one CPP flags variable. And what you can also see is those are standard variables. And I use this append operator to add objects to this object variable. Now let's look at one of those pattern rules. The first rule is building the target. So often you see an all rule there, but if the first rule is the target, then you don't need it. And I would omit it. It only makes things complicated, not required. The first rule is the default rule, period. Yeah? And you don't need any all rule. And the target depends on build dir. Of course, this directory on the initial build is not yet existing, so you need to create it. And there is a rule for that at the bottom of the file, and on all the objects. And I inform you what I'm doing using the info function. And then this is linking the thing. Here I don't use a compiler. I use a compiler, but I don't use, for example, CC. I use the special linker variable. This is because here you can specify in a mixed language application with which compiler you want to link the application. So when your code has a main routine in C, then the linker should be, of course, the C compiler. But if the main routine is a program in Fortran, then you may want to link the code, the binary, with a Fortran compiler. Let's just look for simplicity on one pattern rule. Well, we created here those objects. Of course, we have to provide now a pattern rule that exactly matches those dependencies. So make will look up all prerequisites and then searches for a rule that tells it how to make those. And so we have to specify here build dir. And the first prerequisite, of course, is the stem C. Why don't we have to specify the path here? Well, because vpath does this for us. Yeah. So vpath make will automatically search for prerequisites and then will enter here whatever it found, including the path to it. Yeah. And as an additional dependency, we specify here the include file. I only did it now here for the C. You could also edit it down here. This is when you change the build flags that everything's rebuilt. Yeah, this is usually what you want. And now this is the actual compilation. And then in the second line here, we use the compiler to automatically create the dependencies. So the C compiler and C in general allows this to do that. The flags here, empty says what target should be used, because by default, the compiler will strip off the directory part. That's not what we want. We need the full path in the dependency file. And so we can specify here the target. And the MM, and there are more flags, look it up in the main page, The MM tells the compiler to omit standard system headers. Yeah, so I don't want to depend on standard system headers. Yeah? I only want to have my headers in there. And then I use some special variables. This was here the stem part I mentioned. So this will only use what matches by this percentage, yeah? Or here by this percentage of the target. So it's a stem of the target. No, it's the stem of the first prerequisite. I think that was it. Okay, so finally, I have some phony targets here. You could see them as optional. There is a clean target that will clean all intermediate output. And I have a disclean that will clean everything, including the binary. Yeah. Yeah, I have some targets here. If you need them, that's up to you. Some extra targets like this info target that outputs the currently set flags and the compiler version for documentation purpose, maybe. There is an ASM target that will create the assembly again in this build directory, and there is a tags target that creates with ctags tags you can use in your editor. Yeah, and that's it. So now with dependencies, the last line is what does the magic. Yeah? As I said, I create those dependency files using compiler. Of course, on the initial build, those dependency files are not yet created. And that's fine, because on the first build in C, you don't need any order, yeah? Because every compilation unit is completely separately. And what this line does is, it says, okay, for all objects, if, and replaces the suffix from O to D, if this file is existing, included. Yeah, so as soon as the dependency file is there, it will be included and the dependencies will be used. And this is what we want. Yeah, so on the initial builds, the dependency files are not there yet, but then on rebuilds, and this is where the dependencies are important, they are there. Yeah, and so we only then rebuild the files according to the dependency graph. As mentioned, for Tron90, it's a bit more complicated, and you may need to set up the dependencies explicitly in a separate file, like here in deb.make. Yeah? This is up to you. Okay, so let's have a look. Let's see what we can do there. So just let's call make. This is with GCC, and I have very severe flags there. So it's very picky about stuff. When we look now, you see there is a GCC directory for the intermediate build results, and there is the binary bench GCC. When we look at one here in here, let's look here at the D file. Then you see all the dependencies here that are automatically generated by the compiler. Now, what you could do is you could change this. Yeah, you say, okay, let's build the same thing with ICC. Or again, make. Well, and now we have an additional directory, and you have an additional binary bench ICC. One thing now is, of course, the makefile only acts on the currently set tag. So for example, when you do now make clean, then of course, only the ICC intermediate build directory will be gone. Of course, when you have this question mark, and we will add it in the template, you could say, okay, tag equals GCC make clean. And well, then this does the trick. Yeah, so you could then easily, I know Georg always uses this tag equals GCC because it's more handy than editing the makefile. I usually edit the makefile. It's up to you. Now let's look at one of those include toolchain files. This is the ICC one. We added here the new compiler names. So with the LLVM based one API compilers, the names changed. So you need to specify, of course, the compiler you are using, and then there are some flags. For Fortran, it's very important to specify where the mod files end up. Yeah? So you need to tell the Fortran compiler that the mod files should be placed in this intermediate build directory. Otherwise, they are placed in root, and you don't want that. And of course, you can add whatever you like here in this include file. We use now those include files for toolchains, different toolchains, but of course you can use it for whatever you like, for different operating systems, for different cases, configurations, what you want. Yeah, you can just use it. It's just a tag with a specific configuration. Yeah, so how you use it, this is up to you. Now, what I want to also showcase to you is this enabling the output. You might know. Here, there is no output. And when you want to see the output, you can specify q equals empty. Now the add is gone. And now you will see the actual commands that got executed. Yeah, for example, if you're not sure what happens and so on, you can look at it here. Okay. So now, of course, when we now press make, it says bench ICC is up to date, and now we can showcase, well, what happens if we just touch a file without changing it, like, let's say what is in there, the timing header. And when we remake, well, now, because also of the dependencies, now make knows, and we didn't change it, but make doesn't know that. It only knows that this now has a newer modification time, and it will now rebuild everything that depends on this. And this is the main file and the binary. Yeah, that's it. Yeah, you can also try make info. It will give you the version. And that's actually it, what I wanted to show with the basic version. I don't know, I cannot see the chat if there are any questions. No. So let's have a look at the extended version. So in here, we allow for configuration options, and those are done in config.make. And here we are using to enable, of course, you set the variant, but then you can enable or disable OpenMP and liquid instrumentation, and you can set some specific options here. Yeah, so there are the options. I'm not sure now if OpenMP works. We will see, because I don't know if I have it here installed, but maybe someone notify me when the homes are there again. Still, what we can do is we can look how this is. We can look at how this is implemented. And here there are two variants. The first is the OpenMP flag. This is actually used in the actual toolchain directories. So here in the toolchain directories, you have now this if equal clause, and you check if enable OpenMP is true. And now again, important here is the strip, because if you don't use the strip and you have, let's say, a space here, in my editor, this is marked, but in a lot of editors, it is not marked, then it will not match. Yeah? So therefore, the strip is important. And then we set some specific flags that are required for OpenMP. Yeah, that's it. With Liquid, it's a bit special. We have a special include liquid file here. And the reason is that we set some standard locations for liquid. So we set the liquid define that's necessary to enable the macros. And we use special variables that are also used by our module system. So if you're loading a liquid module on one of our clusters, then those variables will be set in the environment and will contain the correct paths according to the liquid module, and will then be used instead of those default definitions. Otherwise, there is nothing special here apart from that you include here this config.make file. When you look at the source code, And you can see how this is used. Well, here we use the standard OpenMP define. For our specific options, we are using, well, the defines we set, like verbose data set, and we use another one. Yeah? And that's it. Yeah? So that's all the magic. And so you can easily then now configure your build here. You might also want to have a look at this if you are interested how to use liquid instrumentation. Yeah? So this also showcases liquid instrumentation. Let me look, let's build this. So one thing, of course, you can do when we do the default build now, this is without OpenMP. You could override it and set OpenMP. I hope this is right. Was it with underscore? No, I think it was OpenMP equals true. We will see. And make. And what happens now is nothing happens. Yeah, because this is not a dependency, and that's a disadvantage. Or what means a disadvantage? But this is a limited application when you specify the environment variable in the environment, so the variable in the environment, because this is not a dependency to make, and therefore it doesn't update it because bench ICC, in its opinion, is up to date. Now, when we edit this here and set this to true, and now build, now it is rebuilt, because when we look it up in the makefile, config.make is a dependency, yeah, and then it works. Yeah, this is, I think, all I wanted to say for that. So last but not least, let's look at the mixed language example. As mentioned, there is nothing really special there apart from the remark that you need to provide flags to create the mod files in the build directory and to specify the dependencies explicitly in this deb.make file. If you want to see a real example, again, I encourage you to look at this HPC CG implementation and MPI implementation in Fortran 90. Okay, that's it. Now let's go back to the slides. I only have very few slides, so I hope you are patient. So one topic I already mentioned, but we didn't cover up to now, is the toolpaths and library dependencies. So some projects might need specific compilers or tool versions. You might need libraries that are not in standard locations or special builds of those libraries. And to find the correct libraries in the configuration, this can be a difficult problem. And Make does not provide any automatic mechanism to address those problems. Of course, you can implement your makefile to solve those issues, like by specifying dependencies explicitly, but it's not automatic. And there are other tools that try to fill the gap for solving this problem. And the oldest one are the GNU Auto tools. Then there is GNU libtool, and there is CMake, nowadays probably the most known solution to those problems. Script languages and modern languages, like modern compiled languages like Golang and Rust, they come with an integrated package manager. I already said those languages, it's not only a compiler, it's a complete ecosystem. And because that's such a hard problem, they enforce on you certain conventions, and together with the package manager and the built-in build tool, they solve this problem. Yeah? When you ask a lot of people nowadays, especially computer scientists, they would say, okay, isn't this old-fashioned? Nowadays you are using CMake. So what is CMake? CMake is a software for building, packaging, and installing software. It's not a build system on its own, but it generates native build files. So on Linux systems or on Unix systems in general, it will generate makefiles. You could see it as a successor to the GNU Auto Tools. GNU Auto Tools was a pain for many codes. Running the configure script, many of you might remember this, took longer than the actual compilation. And when you had an error, it was very difficult to fix it because you had a lot of complexity introduced. The configure script was a lengthy, complicated as hell shell script. And the makefile also was generated and was also very complicated. And so it was difficult if you ran into a problem, often to convince this tool to do what you know is right. Yeah? And there's nothing complicated. And it's kind of the same for CMake, in my opinion, at least. Yeah, you might object, and I might, yeah. A lot of you might have a different opinion, but that's just my opinion. So the features that are promoted by CMake itself is that it can handle complicated directory structures, can automatically locate system-wide and user-specified files, libraries, executables. It comes with a graphical configuration editor. And as a bonus, it can generate project files for EDEs, so like Xcode and Visual Studio Code. Those use special project files, and CMake can create those project files. So for me, none of those are really solving pressing problems I have. So having complicated directory structures is a bad idea in the first place, yeah? And you shouldn't do it. Then automatically locating system-wide and user-specified libraries. The occasions where I had the fun dealing with CMake, it didn't work. I had large projects which used CMake. I don't know if those people didn't know how to use CMake correctly, but it only caused us trouble. And in some cases, we had to debug for hours just to debug CMake to get this thing to compile. And we knew where all the stuff is. We needed to tell CMake that it accepts that it is somewhere. And usually it was a hack to hack besides CMake to convince it to do the right thing. That's one thing. Yeah? So it adds complexity and it introduces a lot of problems for build and for your users. Yeah? And users, when you download your code and it doesn't build, they will just drop it. Also, what you frequently hear is, I need CMake version XYZ. So a tool that is there to solve dependency problems causes dependency problems itself. Something is wrong there. So I don't see an application there. And I think you have to be very careful in employing this. I know people, computer scientists are religious people, and you will hear a lot of people that say, you know what, CMake is the only solution. You have to use it. That's the way to do it right. Don't trust them. They don't know what they are talking about. And I don't think that CMake brings anything to the table. The only reason I would say is valid is portable build system. When you compile on Linux and on Windows, still you can also implement a makefile that also works on Windows, using Sigwin, for example. But it's more complicated. That could be an application, but all the other stuff I don't need, because I don't need a graphical configuration editor. I have a text editor that's probably 1,000 times better. So nothing of those features bring anything to the table to me, and this thing only causes headaches. So my recommendation is keep it simple, stupid. And I think with Make, you have a robust and portable environment. And for most, I dare to say, all build requirements, you can find simple and robust solutions just using Make. In terms of dependencies, yes, this is a hard problem, but in my opinion, this automatic finding dependencies usually doesn't work. And so I am a friend of explicitly specifying all the dependencies. Usually that's also the way you use configure and so on, because you don't want it to find something. You want to find it specifically something. And if you know where the stuff is, why not write it there explicitly in the text file in the first place? And so the automatic is a promise, but usually it doesn't come for free. It introduces a lot of complexity. And what the main point is, with Make, you implement a makefile one time. Yes, this is an effort. You have to do it, but then you're done, and then it works. With CMake, maybe at the beginning, you might have a working case quicker, but you will probably have constant problems of that because of all this complexity that's introduced by this solution. So Outlook, I think NuMake is all you need for build automation. If you have dependency problems, those can be solved. Keep it simple is my recommendation. Don't overdo it, and don't listen on people saying you need complicated directory structures because that's the way it is done. That's not right. It's a programming language, yes, and it's as always up to you if you use this in a sensible way. Yeah, you can write terrible Perl scripts, you can write terrible makefiles, but you can also do it right. And that's your task, yeah, and it's up to you. It's not the fault of Make when you write bad makefiles. A lot of things I did not cover in this talk. Some of those are in the liquid makefile, or you can look it up in the documentation. The one stop for documentation of Make, and I really encourage you only to look there, are the official info pages. I linked them here. It's great documentation, lots of examples, also has in-depth information on how Make works. It's GNU-Make, sorry, I would add here GNU-Make. And don't search on Google and get on some Stack Exchange thread where some guy tells you some weird stuff. Go there, go to the info pages. All you need is there, and you can solve any problem just with the documentation that's there. Finally, topics for the next HPC Cafe in July. So next month, we want to have a session on Conweer and on news on NHR, so on our new system we will acquire and install this year. In August, we will have no HPC Cafe, but there will be the beginner introduction as usual.